Alright, let's move on to the multi-variable problems. So again, we have two types of problems. We need to find zeros based on multiple variables, or we would like to find the maximum or minimums. Uh, Both of them we are using the same function, which is nlminb or optim. These two functions are used for maximum to find the maximum or minimums, but we can adapt it to find zeros. So for the multivariable, the first example is to solve equations with multiple variables. For example, I have the first equation such that x to the power of y equals 5, and then x times y is 100. The first step we would like to solve the equation is that we would like to solve for zeros. So we can isolate the zero on the left hand side and then move everything on the right hand side like this. And then we can use the nlminb function to minimize the discrepancy between. So we can make the right hand side and square it so that, okay, we would like to minimize x to the power of y subtracted by 5 square. So if this subtraction, let me put up the pen. So if this subtraction is 0, it will be the minimum. So if x to the power of y is greater than 5, the square term over here will be greater than 1. Or if the x to the power of y is less than 5, this square term is also greater than 0. So if x to the power of y equals 5, it will provide the minimum, as well as x times y subtracted by 100. If x times y is close to 100, this square term will be close to 0. So the objective is that we would like to minimize the sum of both terms over here. We can call this method as scalarization. So we have two equations, we make them to the same equation and find the minimize of the sum. So let's make the function. So I call it mul1, which is the function of the vector. This vector will provide two elements, x and y. So the first equation is that the first right hand side is the vector of 1 to the power of the vector of 2. And then we will subtract it by 5 later over here. The second equation is that vector of 1, the first element of the vector, times the second element of the vector, which following the second equation. And then this right hand side too subtracted by 100. Both of them are square, so these are the minimizing function over here. And then we use nlminb. We provide the starting value, which is 5 and 2, and we say that, okay, we want to find the function of the vector by mul1, which is defined above. As a result, we got x equals 366.9 and y equals 0.27. So this is a solution that provides the minimum, but it could have the other solution. This set may be not the single and only solution. And we can see the objective. Objective is the result of function of x and y, which is very close to 0, which is good. And 0 means convergent, and then we need 32 number. The number of the iteration is 32. Okay, let's move on. So what if there is no solution? So I would like to solve for these two equations such that log of x plus y equals negative 100 and x over y is 5. So as we know that log of x always greater than 0. So this equation will provide no solution. But if we would like to make the R to run it anyway, so we can isolate 0 on the left hand side and move everything on the right hand side like this and like this. And then we provide the minimizing function such that log of x plus y plus 100 squared plus x over y minus 5 squared. So you can write the function like this, and they say mul 1e that's supposed to provide the error, and vector again has two elements x and y. So you can follow the equation and you will see you can write out the minimizing function. So I use nlminb. The starting value is 9 and 3, and the function I use to minimize is mul 1e. You see the result. Okay, the nlminb will provide the answer anyway. So there is x and there is y. However, if you see the resulting discrepancy value, it is not close to 0 at all. So you cannot find the solution. Okay? Next, okay, let's say we have multiple solutions. For example, 20 equals x times y and 5 equals x over y. Okay, so we can move everything on to the right hand side and isolate 0 on the left hand side. And again, we would like to minimize xy minus 20 squared plus x over y minus 5 squared. However, in these equations, it has two solutions such that x could be 10 and y could be 2. Okay, 10 times 2 is 20, 10 over 2 is 5, and again we can use negative 10 and negative 2. Negative 10 times negative 2 is 20, and negative 10 over negative 2 is 5. So we have two sets of solutions. Okay, we can write out the equation, and let's say I start the first minimizing function at 9 and 3, and second I start at negative 9 and negative 3. You will see that if I start with 9 and 3, I got the result of 10 and 2, and the objective is very satisfied such that it's close to 0. However, if I start at negative 9 and negative 3, okay, so I got the result of negative 10 and negative 2, and the discrepancy value is close to 0 as well. So again, we have two solutions. Alright, so that's why we could vary our starting values. Okay, so let's move on to missing proportion. The example depends on the context of missing at random, such that the logic of the missing rate depends on the auxiliary variable z, and we would like to specify beta 0 and beta 1. So let's say that both beta 0 and beta 1 are not known, and z is the binary trial, such that the proportion of 1 is 0.5. Again, like previous one, the expected value of z is 0.5. However, in this example, I would like to set up two sets of equations such that when z equals 1, I would like to have proportion of missing equals 0.2, and when z equals 0, I would like to have proportion of missing of 0.4. Alright, so we can substitute 0.2 and 1 for the proportion of missing and C here 0.4 and 0 to the equation as well. So we can set up the equation. I make the right hand side as delta 1 and is equal log of negative 2 over 1 minus negative 2 log of 0.2 over 1 minus 0.2 subtracted by intercept and plus beta 1 1. No, this one's supposed to be negative minus sign, sorry, and this one's supposed to be minus sign as well. Okay, so we would like to find beta 0 and beta 1 such that it minimizing delta 1 square and delta 2 square. Alright, so the function I call it mul2 and the parameter I have two parameters. The first element is beta 0 and the second element is beta 1. False is the value of z, okay, and pm is the proportion of missing. So the first difference delta 1 equal to the logarithm of proportion of missing at the element 1 over 1 minus the proportion of missing at the element 1. Okay, so we can specify the proportion of missing later over here, which can be passed to here. Okay, minus the intercept, which is the first element of the parameter, minus the slope, which is the second element of the parameter, times the first value. So we can set it up again for the second difference, and then the minimizing function would be the difference 1 square plus the difference 2 square. Okay, so we can start using the nlminb function where the starting value is both 0 and 0. The minimizing function is mul2 and the value 0 when z equals 0, the proportion of missing is 0.4, and when z equals 1, the proportion of missing is 0.2. Okay, when I ran the function I got this. So beta 0, the intercept would be negative 0.4, and beta 1, which is the slope, equals negative 0.98, and this would be very close to 0, which is good. So we know that if beta 0 equal to negative 0.4 and beta 1 equals negative 0.98, we got our desired result. Okay, so let's move to the power of independent t-test. So in the single solution problem, a single variable problem, we solve for the part we would like to find the sample size for the independent t-test. But right now we can separate the sample size to the sample size of each group and find the best combination of sample sizes to provide the desired power. So let's solve for the sample size independent t-test. We have a quantity of 0.5, power of 80%, alpha of 0.05, and we would like to have unequal sample size. And this is the same figure that we have on the single variable problem. So again, we start with finding the critical value. So we have the central distribution with n the equivalent of n minus 2, which is the sample size of first group plus the second sample size of second group minus 2, right? So this would be the critical value, and to find the critical value is assigned as qt. The proportion would be 1 minus alpha over 2, and the degree of freedom is n1 plus n2 minus 2. Okay, And next, I would like to find the power, right? So based on this distribution would be non-central T distribution with degree of freedom of n1 plus n2 minus 2, and non-centrality parameter or delta is the coincidence D times the square root of n1 times n2 over the sum of both sample sizes. So we can write down the equation, which is the observed power is assigned as 1 minus the pt proportion of t come from the critical value. Degree of freedom is n1 plus n2 minus 2, sorry, and then non-centrality parameter equals d times the square root of n1 times n2 over n1 plus n2. Okay, so in this case, many combinations of n1 and n2 would provide exactly the same power of zero point 0.8. So this is the graph such that the asymptote of n1 when n2 increases to infinity would be around 35, and the asymptote of n2 where n1 increases to infinity would be 35 as well. Okay, and we would like to find the combination that minimizes the cost function, which, let's say the first group is the treatment group and it is more expensive than the second group. So we would like to gather less of the n1 and more of the n2, right? But we don't know exactly which combination should we pick. So first we can use the scalarization method. So mod3, this is the function I define, which is function of sample size ns, and is the first element would be n1 and the second element would be n2. Pow is the desired power, d is cohency, and alpha is 0.05. Then the critical value is qt again, alpha 1 minus alpha divided by 2, and the degree of freedom would be the sum of sample size minus 2. The observed power is 1 minus pt from the critical value. This is the degree of freedom, and this is the non-centrality parameter. And then we need to minimize two things. First is the discrepancy between observed power and the desired power. And second, we would like to minimize the cost. And the cost is 2 times the first sample size plus the second sample size. And we can provide the scaling constant. And because of the scaling constant, if we put this equals to the lower number or the higher number, it will change the solution. The solution depends on the weights given to each minimizing function. So right now I put 1 over 1000, and I hope that the cost function will be weighted equally to the power discrepancy. And then I use the function nlminb with a starting value of 20 and 10, mod 3, coincidence is 0.5, power is 0.8, and the lower bound would be 2 and 2 for each sample size, each group size. So when I ran this, I got n1 equal to 38.4 and n2 equals 54.7, and the objective is 0.15, which is make me a little curious. So let's see the observed power. Okay, we know that I calculate back and found that the observed power is just 0.65, which is not equal to 0.8 that we decided, and the cost is 131.54 divided by this one supposed to be 1000, sorry. Okay, so the results depends on the scale in rates, and let me change the scaling value, and I will find that okay, if I use a scale of 100, I will find n1 and n2 equal to a very low number which provide very low power. But when I increase to 500, 1000, the power increase but it's not equal to by 8 that I want. But you see, the cost is higher as well. But when I choose the scaling value to be 100,000, I got power of 0.798, which is higher but not equal to zero point 0.8, and the cost is 184. Okay, so the scaling will change a lot, change the result a lot. For the lower scale, it weighs more to the cost, and for the higher scaling value, uh, the power will be weighted more. So wrong scale, if we use wrong scale, we will not get the desired result. So as another method, I change the multiple, I change multivariate, multivariable problems into multiple single solution problems. So first, I would like to calculate n2. No, I would like to provide n2, and I would like to use the n2 to find n1, such that I can get the power of 0.8. So after the first step, I will have the combination of n1 and n2, and then at the second step, I will change the n2 to get the minimum cost. So I will the first to the second step, and then the second step I got the new n2, and then I find the new n1 again, and I got the n1, I provide the cost, then I go back and calculate, change the n2 in order to get the minimum cost. So by this loop, first I need to find n1 given n2. So I call it fun, which is a function that I provide the value of. I would like to find the value of n1 given the power, the alpha, and n2. Okay, this is a critical value that we just discussed, and this is the observed value, and this is the discrepancy between the observed power and desired power. I use the unit root function to get n1. So the boundary of n1 is 5 and 1000. Power is the desired power, d is coherence d, alpha is alpha, and n2 is given. So we know n2, we calculate for n1. And the next step is that this is the thing. Okay, let me clear that. Sorry. Okay, so this is the section that we know n2, and I would like to use n2 to provide n1, right? And this is the cost function. Okay, and the cost function will be used as the result of the function called mul32, and the function mul32 would provide n2 such that it minimizes the cost function. So let's say I start at 50 and I calculate the cost function via the unit root function over here. I get the result, and then I change n2 successively until I get n2 equal to 77.18, which is the minimum. n1 is 54.28. I got the power point of 0.8, and the cost would be 185.74, which comes from here. So this is more efficient, and well, it's harder to write the codes, but the result does not depend on the scale, which is very good. Okay, So example 1, I would like to find zeros, right? As well as example 2. Example 3 would be the mixture between I would like to find 0 for the power and I would like to minimize the cost. But in the example 4, I would like to use nlminb to fit in the multiple variables problems and find whether the data fit a distribution. Again, I use the rating variable in the attitude data. And then I fitting the rating variable with the distribution that has more than one parameter. For example, the normal distribution, I use the density function of normal distribution. X is the vector of the rating variable. Mean of 0, standard deviation of 1 to the log scale. And we like to see if my distribution is the normal distribution with mean of 0 and standard deviation of 1, what is the likelihood of that distribution to be underlying the rating variables. And then I got the likelihood of individual data point, then we can sum it together. So this is the result. Okay, so I use nlminb function to get the maximum likelihood estimate of the degree of fit of the mean and the SD. Sorry. So mul4 would be the function of x, which is the mean and SD of the normal distribution, and that would be the target variable. Okay, so the result would be the mean of 64 and standard deviation of 11. Okay, this is the but it is possible that I got the solution that provides the local minima. Okay, we make that in we keep that in mind, and then we need to test for different starting values. Okay, I use different starting mean and starting SD. I shuffle that to different set of value, shuffle to different set of value. I still get the final mean and final SD of this, and I got the same objective. Okay, when I use 2500 for the mean and 0.001 for the starting standard deviation, I got different result, but the objective is very high. So from this, I am pretty sure that the mean would be 64.63 and final SD would be 11.97. Okay. However, which distribution fit the most? We know from the chi-square distribution and we know from the normal distribution. Okay, so we can calculate the likelihood of both distribution. However, which distribution which fit the most for the attitude for the rating variables? So we can use AIC. For example, AIC would be 2 times the number of parameters subtracted by 2 times the log likelihood. Okay, where k is the number of parameters. So for the chi-square distribution, I got the different value that would be negative 118, and I'm sorry, this would be the 236, right? 2 times 6, 236 plus 2 would be 238, and then for the normal distribution would be 238 as well. So in this case, either one is preferred because we would like to have the AIC as lowest as possible. So from here, chi-square distribution and normal distribution provide similar values. So either chi-square or normal distribution is good. but we can find the next decimal point and see which one is less than which one. Then we pick the less one. Okay. Next, we can find the factor loadings. So we would like to find one set of unequal factor loadings such that it provides the reliability of 0.8. So this equation comes from the example from the single variable problem. Okay. So, and we know that we want to have the indicator variance of 1. So sigma square sub j equals to 1 minus lambda square sub j, assuming that the factor variance is 1. And because we would like to have each variable to be important or quite important variable, so we fix the standardized loading to be range from 0.4 to 0.95. Then we can write the equation. So mod5 is a function of x. X has 5 elements from lambda 1 to lambda 5. And the target is the target reliability would be 0.8. So I put loading is assigned as x, and error variable would be 1 minus the square of loading, and we can calculate the omega. Okay, and we'd like to minimize the difference between omega and the target reliability, and we square that to make sure that if omega is less than the target or greater than the target, it will be greater than 0. Okay, so use nlminb. We provide the starting factor loadings. The function is mod5, and target reliability is 0.8. The lower and upper bound of the loading is 0.4 and 0.95. So we get the value over here. There is the loading. Lambda 1 is 0.93, lambda 2 is 0.496, lambda 3, lambda 4, and lambda 5. Then the objective would be very close to 0, which is very good. However, this problem is under-identified because the solution is not unique. We have only one information, that would be the reliability of 0.8, but we have 5 unknowns. So if we change the starting value, the solution is changed. So let's do that. So if we change to the starting value to 0.45, 0.45, 0.45, 0.5, and 0.9, you will see that the solution is changed, even though the objective is very close to 0. Okay? So the final example, we would like to find the best weight of the sum of x such that it provides the maximal reliability. So that is, we give the weight 1, weight 2, weight 3, weight 4, and weight 5 to individual items. Usually, we will provide equal weight, which is 1. So it provides weight 1 equal to 1, weight 2 equal to 1, until weight 5 equal to 1. But, okay, right now we would like to provide different weight. And the reliability can be calculated by this formula. Okay? The weight vector prime is the transpose of the weight vector times the matrix multiplication of lambda and lambda transpose, then multiply it by the weight over the same thing, but we change lambda and lambda prime to be lambda and lambda prime plus theta. So this would be the variance from the true score, and this is the variance of the observed score. Okay? So W is the vector with weight 1 to weight 5. Lambda is the vector of lambda 1 to lambda 5. And theta would be 5 by 5 matrix such that the diagonal element has lambda 1 square, lambda 2 square until lambda 5 square, and all diagonal elements are 0. So for example, I would like to find the weight of the second to the seventh variable of the attitude data. So right now we have 6 items, right? That provides the maximal reliability. So let's go. The library Lavaan, so we call Lavaan to run factor analysis for us. Then I select the data. That is the second to the seventh variables of the attitude data. I name the columns to be y1 to y6, and then I make the function called mouse6, the function of the weight. But the weight over here, I only provide weight 1, weight 2, weight 3, weight 4, and weight 5. I do not provide all 6 weights because if you see this line, I would like to set weight 6 so that the sum of all weights sigma w equals 1. Okay, so if we know weight 1 to weight 5, weight 6 can be calculated based on the fact that sum of w is 1. Okay, p is a okay, and we provide that, which is the data set. Okay, p equals to the number of columns in the data set. That would be 6 right now, and the script is okay. Factor is divided by y1 to y6, and I call the Lavaan function, the CFA function from the Lavaan package. I provide the script, data equal to that, and I make the latent variable to be standardized, that is the factor variance is 1. I get the random y, which is I call the inspect of the result, and coef that provide a different matrices. Then I get the lambda for the factor loading matrix, and th, that would be the theta, would be the error covariance matrix. The implied, the true variance can be found by lambda y and multiplied by the transpose of lambda y. And the numerator would be the weight, transpose of the weight times the implied from above line times the weight. And the denominator is the same. I just change from implied to implied plus th. And I would like to, and the nlminb function will provide the minimum value. So instead of provide only numerator over denominator, I subtract it from 1. So that I would like to find the minimum of this line. Okay, nlminb is a function recorded, and then the starting value is 1 5 times, and mouse6 would be the function that is the attitude data that we select only second to the 7 variables. Okay, we can run that, and we get weight 1 to weight 5 like this, and I can try different starting value to make sure I do not get the local minima, right? And we know that this one is 1 minus numerator over denominator. Okay, we can subtract it from 1 again, and we get the derivative of 0.88. Okay, I have tried the following line many times to make sure that the result is not the local minima. So I use the run if function. I draw 5 numbers from uniform distribution from 0 to 1 I run this again and again and again, I still get the same result. So it means that the result is good. Okay, thank you. Please leave your questions or on the comment section of this video. So your question will be very helpful to me and other viewers. Thank you very much for listening.